Welcome everyone to this week's ICTS String seminar. We have Shahin Sheikh-Jabbari from IPM Tehran. He's going to talk about null surface thermodynamics. Over to you, Shahin.
Thank you. Thank you very much for the kind invitation. I'm going to tell you about the work that we have been doing in collaboration with people who, some of them are in the audience and you can see their names. This is what we have been working through in basically different projects in the last about 2 years. And basically, let me give you a one sentence summary that basically we find that laws of thermodynamics naturally appear whenever we have in a gravitational system, whenever we have a boundary. So that's basically the bottom line that I'm going to basically go through the equations and establish this. So just by the way of introduction, the relation between gravity and thermodynamics is very long-standing, and it has appeared in various different realizations. So maybe the most interesting and feature for gravity, very distinctive feature for gravity, is that it's universal in the sense that it's a kind of interaction that any object, by the mere fact that it has an energy momentum tensor, just contributes to gravity. And thermodynamics is similarly very universal, regardless of details of any system that any stat-mech system that we want to study. It shows thermodynamic behavior. So the universality is basically what these two formulations, gravity and thermodynamics, share. And of course, the relation between the two has been established in some different contexts. Maybe more famously in the context of black holes, where starting from the seminal work of Carter, Barden, and Hawking in early 70s, and so followed by the work of Bekenstein and Hawking, and then which was put in a more formal setup in Wald's seminal works in 93 and 4. And then meanwhile, right after this works of Hawking and Bekenstein, there was the work of Unruh, which basically related the thermal behavior to any accelerated observer. And of course, the relation between accelerated observers and gravity is coming through the equivalence principle. So it was sort of in the same trend. And then there was another twist in this line, which came in the work of Jacobson. And what he did was basically he started from thermodynamics and tried to derive Einstein equations. So the previous works was basically starting from some gravitational system, typically a black hole, when we have a horizon, and basically find some thermodynamic description. But Jacobson basically reversed the story. Then there was some other works, some ideas have been around. For example, this gravity as entropic force by Verlinde, which was sort of trying to give a different angle in the relation between gravity and thermodynamics. And of course, there is a huge literature on the holographic principle and ADS-CFT and black holes, and there are experts in the audience on this very aspect, which relates basically gravity and thermodynamics. The kind of setup that I'm going to study here is basically, I'm asking the question of formulating gravity on spacetimes where we have a boundary. So basically, when in the presence of boundaries in spacetime, typically what we need to do is to include the boundary degrees of freedom, and These boundary degrees of freedom are there to ensure specific boundary conditions that we may want to impose on the system. Basically, one can ask, how can we systematically formulate these boundary degrees of freedom specifically in a gravitational system? So that's the kind of question that I'm going to formulate and study. And by boundary in particular here, I mean any codimension one surface. In this example that I'm going to study, I'm going to take a null surface, but it could be a time-like or space-like in general. It could be sitting at the asymptotic region of the space-time, or it would be an arbitrary place in the space-time. In gauge or diffeomorphism invariant theories, like the gravity case, one can ask, how does the gauge transformations or the diffeomorphisms act at the boundary? And basically, among these non-trivial diffeomorphisms, and by non-trivial here I mean those which non-trivially act at the boundary, one can associate some conserved charges, some surface charges, and if these surface charges are well defined, we can basically declare that these part of diffeomorphisms are non-trivial, and one can use these non-trivial diffeomorphisms or associated surface charges to label boundary degrees of freedom. In the context of black holes, this boundary or asymptotic degrees of freedom have been proposed to be relevant to black hole information problem. Maybe most famous proposal in this direction is the one by Hawking Perry-Strominger, but there are many more within the same set. Okay. Here is the outline of my talk. I'll basically take you through the formulation of the problem that I just mentioned. And in particular, I'll focus on the null surfaces, which are models for black hole horizons. And I go through basically a computation of surface charges and boundary symmetries in generic d-dimensional vacuum Einstein gravity. And through this analysis, I basically show you that there is a natural description of these boundary degrees of freedom in terms of local laws of thermodynamics at the boundary. And basically, I'll summarize and give you an outlook how this could be extended or be more relevant to black hole physics. So let me just briefly review the problem of gauge theories in presence of boundary. So let's suppose that we have an action which a d-dimensional action of a gauge theory defined on a manifold M. And by gauge transformation, I mean this generic fields phi are basically rotating at each and every local region in space-time in this way by some gauge algebra, and the action remains invariant. But and of course, in gauge theories, as you very well know, the physical observables are gauge invariant quantities, and to treat these systems, we fix the gauge symmetry, which are basically redundancies in the description. And the point is, even after this gauge fixing, there remains some measure zero subset of the gauge transformations, which act at the boundary in a non-trivial way. So in particular, let's suppose that we have the boundary value of the fields, phi alpha, denoted by this curly phi. The variation of these fields basically induce a variation at the boundary value of the fields. And these phi alphas could be non-trivially transforming at the boundary. So, and basically the question is whether we can associate conserved charges to these variations and these residual symmetries, gauge symmetries. So let me give you an example, a very simple example, just to illustrate how it works. Consider, for example, Maxwell theory in a box. This box could be a perfectly conducting box or any other region of the space-time. It could be a physical I mean, partition between this box and the outside, or it could be just some arbitrary box that you can imagine in the space-time. But for any reason, if you're interested in formulating physics inside this box, we need to assume that there are some degrees of freedom which are residing at the boundary degrees of freedom. Basically, there should be some boundary currents associated with this boundary degrees of freedom. This is what we are very familiar with in the standard courses of electrodynamics. And these boundary currents are to ensure the basically appropriate boundary conditions on the electromagnetic fields in the box. So if we have a physical boundary, like a perfectly conducting box, there are, for example, electrons or matter at the boundary, which basically provide me with this boundary currents or boundary degrees of freedom. But the question I'm asking is whether we can formulate the same problem of finding and identifying boundary degrees of freedom without basically ever mentioning what we have at the boundary. I mean, without recrossing to the fact that we have electrons and other stuff at the boundary. And the answer is yes, and it comes through this surface charges that we have and the non-trivial gauge transformations. And this is somehow providing, this setup is providing me with a microscopic description of what would have been there if I had, for example, perfectly conducting plate and the electrons there. So basically, this is the kind of example that we are all familiar with. And there are two different ways of formulating the question of boundary degrees of freedom. One is just without resorting to having anything specific, any other in the field at the boundary. And the other is through the boundary gauge transformations, non-trivial gauge transformations. And the second is the one that I'm going to use and formulate in the context of gravity. So as we all know, Einstein GR is a generally covariant or invariant field, depending on whether you look at the equations of motion or reaction. And the physical observables are diffeomorphism invariant quantities. And under generic diffeomorphism, C mu, metric transforms in this way, which you're all familiar with. And usually a part of these diffeomorphisms is fixed when we fix an observer. But typically when we choose a coordinate system, we fix a part of these diffeomorphisms. And usually there are some residual parts. So let's go through the equations of motion and just do a simple counting to see what's the room that we have for boundary degrees of freedom if we want to formulate the theory in a space-time which has a boundary. So in d-dimensional space-time, metric has d times d plus 1 over 2 components. Out of this, in pure Einstein gravity, d times d minus 3 over 2 are propagating gravitons, and d number of them are diffeomorphisms, or would be fixed by the diffeomorphisms. And the similar counting goes for the field equations, Einstein field equations. There are d times d plus 1 over 2 number of them. There are d times d minus 3 over 2 second order differential equations. These are corresponding or governing the propagating gravitons. And then there are d constants. So these are first order equations. Okay, so the most general solution to these Einstein equations are hence fully specified by Is there any question or comment?
Oh, I'm sorry.
Okay. So the space of solutions for this system is specified by a boundary and initial data that we basically put at the given Cauchy surface, for example, or constant time constant time slice. And in general, it involves 2D number of functions over the codimension 1 boundary, plus, of course, the propagating gravitons. So this is just by simply looking at the Einstein equations. That's how the counting goes. So we have bulk degrees of freedom, and then we have boundary degrees of freedom, and there are 2D number of them, which are functions over codimension 1 boundary. Okay. So for the example that I'm interested in, namely those which are related to the black hole horizon, the null boundary is the appropriate one, which can model the horizons. For example, in this Schwarzschild black hole, we have this horizon, H plus and H minus, and these are basically the boundary of for the observers who are residing in this region 1, in this bluish region. So any observer who is never crossing this to the other side of the horizon would see this as the boundary of his or her spacetime. So the question I'm asking is, how can we formulate gravity in this patch of the spacetime without ever talking about what we have behind the horizon or on the other side? Okay. So this is the motivation. But we can formulate it in a more general way. Let's suppose that I take the boundary of my space-time to be this sigma, which is a null surface. It's codimension 1. I adopt the coordinate system where this null surface is sitting at r equal to 0. And I'm going to formulate physics in the outside region, which by that I mean r bigger or equal than 0. So I just want to excise this part r smaller than 0 from my space-time and only focus on this region, the outside region, and formulate gravity theory on this part. And in order to do this in a consistent way, besides the gravitons, which are basically moving here, they could be infalling or outgoing, in the future-oriented ones, I need to introduce some boundary degrees of freedom which are residing on sigma. And the question is how we systematically do this. Okay, so once again, I want to excise the r less than 0 and formulate gravity theory only on one side. Okay, so let's start with some equations. This is the most general form of the metric that I can write. In the coordinate system where r equal to 0 is the null surface. And this condition basically implies some relation between these coefficients of the metric, f, eta, hij, and gi, which is basically this relation. And just as a matter of notation, I'm using the coordinate system r, which I introduced. V and xi are basically the coordinate system which parameterize the null surface. Xi's are transverse to this plane, and this red line is parameterized by V. So that's the choice of my coordinates. And these coefficients, f, eta, h, and g, are in general functions of all coordinates. But in order to make sure that this satisfies Einstein equations, I need to take eta to be r independent. So this eta is r independent, but the others, f, hij, and gi, are depending on v, r, and xi. And in this setup, the notation that I'll be using is this I coordinate is basically running from 1 to d minus 2, which is basically parameterizing the transverse space and the codimension 2 transverse space. And when I use vector, tensor, and scalar, I mean with respect to this d minus 2 dimensional transverse space. Okay. Okay. So
Shahin, I want to ask a very basic question. So,
Yes.
how does one define R equal to 0 in some diffeomorphism invariant way? I mean, if I start at infinity, is there a sense of what R equal to 0 is in some diffinvariant way?
Okay, so it is not diff invariant, of course. I'm bound to choosing one specific coordinate system. You're right, but I'm doing it in a very minimal way. So, just maybe it helps with the question you asked. This R equal to 0 could be any null surface that I have in anywhere in the spacetime. It could be horizon of a black hole or a stationary black hole or elsewhere.
I see. So let me ask it another way. I mean, is the analysis going to be perturbative about a given background?
No.
I mean, it is not good. I see.
No.
So then I'm a little confused. So let's say I start at infinity in asymptotically flat space. And then, so now R equal to 0 was something in this coordinate system, but maybe I do some big transformation, like I have a big black hole forming in some other part of space. So, I mean, is there a sense in which one can relate what is R equal to 0 in the original metric with R equal to 0 in this new metric? I mean, what is the invariant way of making that relation?
Okay, so that's a good question. Can I answer this question towards the end?
Sure, yes, yeah.
Because I need to build up a little bit of these equations to be able to more concretely answer
Okay,
them.
sure, thank you.
I'll come to this. That's a very good question. So basically, I need to construct a solution space. As you can see here in writing this metric, I only impose the condition that R equal to 0 is a null surface and nothing else. So here, these functions f, eta, h, and g are subject to this condition, which is basically reassuring that R equal to 0 is a null surface. Besides that, there are this number of functions there in my metric. In particular, there are three scalars, f, h, and eta, one vector g, and one symmetric traceless tensor. Here, h is basically determinant of this hij part, and this capital H is basically the part which is divergence free. Or the determinant of this hij is 1. So this is, and these functions are still functions of all coordinates except this eta, and I need to impose Einstein equations that I'm going to do next. But I impose these Einstein equations in a perturbative way around R equal to 0. Okay, so if I just go through the equations, that's what I'll get. So this is the result of some detailed analysis. I don't show the details of this, but I'll be happy to discuss them. These HIJs are, in order to specify them, I need to, this is once again, as an expansion around R equal to 0. And these are satisfying second order equations. And in order to specify them, hij as a function of r, v, and x, I need to specify the value at r equal to 0 and the value of its derivative at r equal to 0. So these are the kind of initial data that I need to provide you at this surface sigma in order to specify this propagating gravitons, if you wish, all the way through the bulk. For the vector mode, GI, we have first order equation R, and basically it's completely specified by its value at, since it's first order, but if I specify the value of this GI at R equal to 0, it's completely specified. And then I have Raychaudhuri equations and the null condition that I just showed. And basically, we can solve it for f, and we remain with h and eta. So out of these three scalars, I 2. The vector is again the same mode GI. And then I have 2 of these propagating gravitons. I mean, 2 functions at the boundary. It specifies the propagating gravitons. So therefore, the full perturbative solution space is governed by these functions that I just mentioned. Just their number is d times d minus 3 for the tensor modes, d minus 2 for the vector, and 2 scalars. And in this analysis, I have only assumed the smoothness of the metric at r equal to 0 and nothing else. And in particular, I have not imposed any fall-off behavior or any other restriction on the metric. And that's it. So that's basically the only condition that I have used.
Sorry,
Mhm.
can I ask a question?
Please.
What is omega in your?
Omega is the same as h. It's determinant of this metric hij,
Okay.
or the
And you
square root
assume,
of it.
right. And you assume that these quantities are finite at the boundary, right?
Yes, yes, yes.
And
That's what I'm assuming.
this is kind of a boundary condition, no?
Well, since r equal to 0 is not a specific point or a specific region, it's only a null surface. You may call it a boundary condition, but it's not typically what people take as boundary conditions usually.
Okay, thank you.
Mm-hmm.
Sorry, just to understand, Shane, what you're doing. So you call some point r equal to 0, and if the metric fluctuates, you just trace the null surface that goes on in the future. So if I give you some initial data, you will just call the evolution of the null surface r equal to 0.
Yes.
That's why it's not a boundary condition. It's just,
yes.
Whatever the surface does is determined by the equations, and you just call it that. Is that right?
Yes, yes, yes.
Okay, thank you.
Exactly, exactly. And now maybe I can answer your previous question. That here I'm not assuming that this r equal to 0 is at infinity, because at infinity I need to sort of modify some of these arguments, in particular about the smoothness and the expansion around infinity. I need to be more careful. But in this talk, I'm not talking about scribe class, for example. That's another null surface, but which is not fully covered by my analysis here. But other than that, this expansion, as long as this smoothness condition is satisfied, I think is okay. And one can show that although I showed you the perturbative analysis, all the other higher orders in R, if we make a Taylor expansion of all these coefficients of metric, if metric coefficients are Taylor expandable, all higher orders would be basically completely specified by what I just mentioned here. In order to basically completely specify these Taylor expansion modes, I don't need to introduce any extra degree of freedom. There's another hand up. Please ask the question.
Yes, I wanted to ask you, what assumption do you make about the matter in the vicinity of the surface r equal to 0?
Okay, that's a very good question. Here I'm considering pure gravity, pure Einstein gravity. I don't consider T mu nu on the right-hand side of Einstein equations. But in principle, one can also extend this analysis by the addition of matter.
Thank you.
Please, Stefan?
Yes, sir. I had a question. If in the boundary condition, if we have some Hawking radiations and some and some island entanglements, will that change anything?
Okay, so this is only a classical treatment of Einstein equations. So I have basically started with this ansatz for the metric, in which I've only used r equal to 0 as a null surface, and I'm imposing Einstein equations. So it's just classical Einstein equations. So I don't know if I answered the question or not.
Thank you, sir.
Mm-hmm.
Sorry, maybe it doesn't matter. At some point you said something about expansion, but if you don't assume the expansion is positive, it probably doesn't matter, right? It's just something negative, something that violates some.
That's true, but I just didn't want to complicate this analysis here. So these are the comments that I'll make after I establish the role of expansion and other things here. That's true. Yeah. Okay. So just going on with this analysis of Einstein equations perturbatively imposed on around r equal to 0, I can reparameterize the functions that I had in this way, which is more handy. I consider an expansion around r equal to 0. This f function, which if you remember is the dv squared coefficient, starts from first order in R. It doesn't have the 0th order. This is basically the having a null surface at r equal to 0. This g, I expand it in this way with the coefficient j, and the hij is expanded by omega and higher orders. But these functions which appear here in the expansion are of course only functions of v and xi. These are functions over the C. So a bit of notation and conventions. This omega ij, which is basically the metric on this codimension 2 surface, and the v and r, constant v and constant r surface. I take out the determinant of the metric and call it little omega, and the rest are gamma ij. And I can define the dv, curly dv, is the covariant derivative along this v direction, and basically this is lead derivative along this vector g. And as Subrat already mentioned, one of the key geometric objects that I'm going to use extensively in this analysis is the expansion of this the null vector field, which generates this surface n. In terms of this omega is basically given by this expression. So this is the expansion of this null surface. And then the News tensor, which is basically measuring the flux of gravitons through this null surface, these null rays, are basically specified by this Nij. And you can easily see that this Nij is traceless transverse. So this is my graviton mass. And this is also related to the previous question. Even if I have a Hawking radiation, it could be at this semi-classical level that I'm considering could be parameterized and captured through this Nij. Okay, so then these are the Einstein field equations, which are projected at r equal to 0. These are the equations that I need to solve for these functions which appear in the expansion of the metric. Okay, so this is the v derivative of these objects, omega p, which is the log of eta over theta squared. Eta, remember, is basically this term in the metric, the dr dv. You can think about this eta as the basically your time scale. So and the log of it is appearing as this p, which should satisfy this equation. So these are basically the Ray-Chaudhuri and Damore equations, and this is the definition of expansion theta. Okay, so
sorry, I have a question.
Please.
So when you say you have Einstein field equation, you mean with the cosmological constant switched on or off? I mean,
well, in this analysis, it doesn't appear, but we have not considered that. But even if we had, it would not have appeared here. The reason is sort of simple, that we have this r equal to 0 And we are expanding Einstein equations locally around this R equal to 0. And locally, I don't expect to see the effects of cosmological constant in generic d dimensions. But we have not, in these equations, we have not considered lambda cosmological constant explicitly. But it would not have changed any of my results.
Okay, thanks.
Okay, so the solution space is hence parameterized by these functions, omega pj and nij, and the derivative of this hij at r equal to 0. This is basically the number of functions over sigma that I need to specify the most general solution up to this smoothness condition that I consider. And then the rest of the functions like gamma and theta and others would be basically functions of these. Okay, so here I've basically perturbatively constructed the solution space. I already told you that I've chosen my R coordinate partially such that R equal to 0 is a given null surface. The rest of the diffeomorphisms, which I have listed here in equation 4, basically parameterized by this t, w, and yi, is keeping the R equal to 0 as it is. So the null boundary is not changing by this. In particular, note that, for example, this one is a scaling R, and these ones are only acting as diffeomorphisms on this sigma. So none of them are, it's just very visible that one do not change R equal to 0 with these diffeomorphisms. But the point is, upon these diffeomorphisms, this one solution in the solution space that I just showed rotates to another solution. And the number of functions that I have here is, by functions, I always mean functions over sigma. So I have t, y, w, and yi. So I have d minus 2 and or one vector and two scalars. Basically, as I just mentioned, these transformations, which rotates me within the solution space that I just discussed, acts on the functions in a very simple way that one can work out. And just going back here, as I told you, I have my bulk graviton modes and the boundary modes, omega p and j, and these are the bulk modes. And the rest of them, and this omega p and j, are associated with the boundary modes. Okay, and the number of the boundary modes that I have, namely 2 plus d minus 2, is exactly equal to the number of functions that I have in my non-trivial diffeomorphisms. Okay, so basically, this means that if there are some charges associated with these symmetries, these are symmetries in the same sense that we have in the Noether's theorem, because they are rotating me in my solution space. If I can find the Noether charges associated with these symmetries, I can use these charges to label the boundary degrees of freedom, which have the same count. So that's the general idea. Okay. So just to summarize, we have propagating modes, graviton modes, which are encoded in nij and h prime, and the boundary modes, which there are d number of them. There are 2 scalars and 1 vector. Okay. So it's a bit of technical stuff that I take you through them. Basically, I want to establish that this solution space that I just described, constructed, is a phase space. And in particular, there is a well-defined symplectic form acting on it. And to do so, I use the covariant phase space method formalism. Basically, these are the standard, formulations to construct symplectic form for a given theory. Here, the Einstein graph. Okay. So once I have the symplectic form over the solution space, I can compute this two form by contracting one of the legs of this two form with the transformations generated by my symmetries, here T, W, and Y. And basically, I end up with one form over the solution space, which need not be a closed one form. This is the delta slash Q. And these are the Hamiltonian generators for this symmetry generators psi. This is, if integrable, these are basically defining my Noether charges. So that's basically the same concept as the Noether charge. Within, now I'm using this covariant phase space method. That's just sort of technical aspect of it. And basically, these charges are given by integrals over codimension 2 surface integrals, basically integrals over this any constant v slice of my sigma. So the charges that I compute here, or the charge variations that I compute here, are functions of v in general.
I have a question.
Please.
The NIJs, they were initially the bulk modes, right?
Yes, yes.
So you are considering the boundary values of those bulk modes here, right?
Sure. Yes.
But in general, shouldn't the boundary values of the bulk modes match with the boundary modes themselves?
And
how can you have different boundary modes corresponding to the bulk modes? And
no, these are basically, let's suppose that I want to consider, for example, a simple question of propagation of, for example, photons in the space-time. You need to specify their initial value on a Cauchy surface and then let the Maxwell equations evolve, right?
Yeah.
And this Nij is exactly those. But, actually, if you noted here, I had this H prime and Nij was standing for this H, Ij. So the H prime do not appear in this, only Nij appears. And the reason is sort of simple, because here I'm considering null surface and I can only have infalling modes. Those which are propagating along this are not appearing there.
Okay.
Mm-hmm. So, but then the rest of this, omega, J, and P are basically some genuine boundary degrees of freedom. Of course, they interact with these bulk modes through these equations that I just showed. So you can view this as basically these equations as the equations which tell you how the bulk modes, Nijs, interact with the boundary modes labeled by omega and P and J. So this is how you can read these equations.
Okay.
But they are accounting for independent degrees of freedom. So just going back to this charge variation, the charge variation, one of the questions that one usually faces in this setup is whether these charge variations are integrable or not, whether I can define charges, not only charge variations, as you can see here. And the answer is no. In particular, if we have a non-trivial flux through the boundary, the charges are not integral. The surface charges are not integral. And we need to develop a technique, which is, there are different ways to do this, which separates flux part and an integrable part of the charge. And we have done so such that the integrable part of this charge variation matches with the standard Noether charge. One can always do this. So this is a non-trivial statement. And besides us, there are some other papers by Friedel and company and Robert Lee and collaborators, which try to establish the same statement. But here I take it just as a statement. So suppose that this is true, that the integrable part could always be matched with the Noether charge. And the Noether charge is given by, is there any question?
Hello? Yes, yes, sorry. So when you're doing this covariant phase space formalism, are you adding boundary actions at your null surface?
That's a very good question. I don't, because I'm not worried about whether I have a well-defined variation principle or not. But in principle, one can do this. Here, I don't do that. Can we discuss this later?
Yeah. Okay.
But here, the short answer is here, I'm not worried about the variation principle. And the reason I'm not worried about is that I assume that there exists a boundary term that I can add to my Lagrangian to account for any boundary variation I want to set to 0. Okay. This is also related to this issue that, or the fact that I mentioned, that the integrable part of the charge could be always made equal to the Noether charge. This is at technical level is related to this question. So thank you for the question. Okay, so the Noether charge is given by this expression, which there are 3 kind of charges: the one associated with W, omega, the one associated with Y, and the one associated with T. So these are the 3 charges that I have. And the non-integrable part, the flux, has this form. One important technical point is that here it's up to me to choose whether I take W T or W minus gamma T to be field independent of the fields that I have in my solution space. That's my choice. So here I am choosing, and this is very important in basically whether I have integrable charges or not, this choice. Here I'm choosing T, W, and Yi to be field independent. But one should remember that this is a choice. And here, as you can see, that P and Ni, J do not appear in the Noether charges, but appears in the flux only. Okay. And if you look at this expression, the 0 modes of this, when I set W, Y, or Yi or T equal to 0, these are the 0 mode charges that I get. And the total charge for this generator d by dv is given by this expression. So these are basically the expressions that I'm going to use in reading of the thermodynamical laws. And one can show, this is just some simple fact, that as I mentioned, these charges are functions over this null surface. In particular, they have V dependence. And d by dv of these Noether charges is on shell is equal to the flux, which passes through. And this is probably related to one of the questions that I was asked. If I have a flux through this surface, I don't expect that these charges are conserved. And the variation, the time variation of these charges should be equal to the amount of the flux which passes through this. So this is basically captured in this balance equation. So, okay, so far so good. I just gave you a description of this solution phase space and label these different solutions with some surface charges. Now, let me very briefly review some very.
I can ask one more question, Shahin?
Please,
So
please.
if I'm understanding so far, as you say, you can define these charges, and there's a constraint equation which projects onto this, which gives you, I think, 10, right? This will just come from the bulk constraint equation projected onto the boundary.
Yes.
I mean,
Yes. Yes.
okay. Now the issue is about, if you look at the energy, for instance, is it clear that the energy, or the charge corresponding to time translation, so is it clear that there's any positivity associated with it? At asymptotic infinity, there's a positivity of the ADM Hamiltonian.
Yes. Yes.
Now, how do we know that this charge here is positive?
Okay. So here, if you look at this 3b, specifically since you asked about the energy, this n squared with this prefactor theta is actually the amount of the energy which passes through the boundary.
Right, and there's a right, but this is probably with the minus sign, right? It's telling you how much energy is going out.
Well,
I don't know what the sign
passing through. Yes, it has one sign only. Yes.
Right. But the question is the quantity P a positive quantity? The ADM Hamiltonian at the past boundary of null infinity is positive. That's the positivity of energy. Now, so there's a similar constraint one gets at Scri plus, right? Which is exactly this. But there's some Christodoulou-Kleinemann condition which says that at the future boundary, this is 0. You can look at space-time where it's 0. And therefore, once you integrate n squared at the past boundary, you get a positive quantity. Here, I'm confused about, there doesn't seem to be a condition that says that at v equal to infinity, p should be 0. So it's not clear to me that p should be positive at any point. I mean, at all points.
Well, about the sign of p itself, I don't know, but the variation of it is always positive.
That's the statement that the flux is positive in some.
Yes.
Right.
I'll make this a comment on this in the next slide.
Right.
These questions are very good and relevant, and I'm going to show you through my thermodynamic description. I think I am running out of time. We can go on for longer, so there are many questions. Okay, so sorry.
Let me just ask one more question on that. So this is one case where Hawking radiation will be important, right? So you have n squared, but if you were to add matter, presumably you would get PVV, a contribution which is proportional to.
Yes.
And then depending on whether that is positive or negative, you could get a plus or a minus sign there, right?
That's right. But actually, the Hawking radiation, I think a more natural setup to describe it, since you asked, sorry, let me show. Actually, when we want to consider the Hawking radiation, more physically, I need to consider not a null surface, but a time-like surface, which is very close to being null, something like an stretch horizon. Once I added, consider that stretching, then there could be outgoing flux.
Right.
Here in this null surface, I don't have this because it's null. So if I do it for a stretch horizon or some slightly time-like one, I'll have the other side. So this is actually another project that we are currently working on to basically replace this null surface with the causal surface, which allows for things, flux also leaking out.
Thank you.
With exactly the same motivation. Please.
I have a related question.
Please.
The black hole mass usually is positive only when you measure it at infinity, right? The ADM mass. For instance, if you are considering the null surface to be a black hole, then is it necessary that the mass or the energy measured at the null surface also be positive?
Oh yeah, yes, of course it is. So basically, let's suppose that we have a stationary space-time, so that I have a time-like healing vector, just to make the answer more precise. I can define a charge associated with this Killing vector, and I can match it with the mass at anywhere. I don't need to go to infinity to define, at least for the stationary spacetimes, to define the mass. And one can show that as long as this time direction is progressing, this is positive. Or at least you can set the origin of the zeroth of the mass to such that this is always positive. It has one side. So, but the answer that I gave was very precise, but only for stationary spacetimes, which I think the class of black holes that you had in mind fall into this.
Okay.
So the short answer is I don't need to go to infinity to define the mass. And as you can see, these charges that I have defined, if they're conserved, by conservation, I mean their V derivative is 0. And that happens when this flux is 0. They are defined at this null surface, which is an arbitrary null surface in the spacetime. And these charges are well defined. So this technique, associating the charges with these symmetries, is very powerful, and it basically relaxes using infinity as the region that you define the charges, like the mass or angular moment.
For instance, if you have the black hole surface, there would be a flux across a black hole surface, right? So, but there wouldn't be a flux across the across null infinity, right? So the charges at the two surfaces would in general be different, right?
So the case that you are considering is not a stationary case because you have gravity waves.
Yeah.
So the precise answer that I gave was for the stationary cases. Yours is more physical, but less precise. I mean, my formulation is less precise for this case. But for this case, I can use the formulation that I'm just talking about here. Then I need to account for the amount of the
continuity
flux.
equation, right?
Yes, yes, and this basically this equation that I call balance equation, you can view it as this is equivalent or a different way of writing Einstein equations at the boundary. These equations. So these are that equation has the same content as this, but is written for other set of variables. This set of variables are fluxes and the charges. So the content of this is exactly the Einstein field equations at the boundary, which contains the one that you described, that basically it accounts for how much energy is passing through this null surface.
It is like a continuity equation, right?
It is, it is. So this is again, Ray-Cheddary equation is one of those continuity equations and is included here.
Yeah, so in general, if you have a flux through a surface, it doesn't necessarily mean that the charge is conserved on that surface. And so
it is not conserved, yes. And this is the same equation.
Yeah, and in that case, it can be anything. It can be positive, negative, whatever.
But again, if the flux can only pass through, for example, to R less than 0, then it has a specific sign. But if it can leak out, then it has both sides.
Yeah, so that's what I'm saying.
But for the null surface, it can only pass through once in one direction.
Why is that?
Oh, because it's a null surface. So just maybe this figure can show you. So things can go, I mean, null rays can fall in. Those which are basically moving outward towards asymptotic infinity are always moving on this sigma. They don't pass through. Just by the mere fact that we have considered null surface.
Okay.
So I have a question.
Please.
Sir, if the null surface infinity black hole is actually a part of a wormhole, then how similar will the two spacetimes be? Even if you consider the dynamics of the noisy charge? Yes. This one.
So short answer is, if I understood the question correctly, I'm basically trying to formulate physics only in this bluish part.
Yes.
And these are the boundaries of the space time that I have.
Yes.
But in order to do so, and in particular, actually, this is maybe an overestimation of, I'm overstating of what I'm doing. I'm only considering this part of it. So, right, not even the H minus. And here, actually, I want to explore the situation where, I mean, formulate this problem such that I don't need to tell you anything about this other side, this region. But instead, I'm putting some boundary degrees of freedom here. And these boundary degrees of freedom are supposedly added such that they account for all the physics that I would have in other side. Okay, so this is basically the name of the game that I'm playing. I'm just first introducing this boundary degrees of freedom, tell you how to label them by the surface charges, and then these equations tell me how they should react to the stuff that I have in the bulk, such that I can basically excise the region in the R less than 0.
Okay, sir. But if we consider the dynamics of the noether charge, will it have any kind of effect on the other side, on the other null surface?
By other null surface, you mean H minus or this one? So
the H plus on the other, the H plus on the other side.
Okay, so I don't need to tell you anything about that. That's exactly what I'm trying to do. I'm trying to detach the dynamics, whatever which would have been there, and basically introduce whatever I need to make this consistent. And these are the set of boundary degrees of freedom.
Okay, thank you, sir.
I could have done this from the other side viewpoint, an observer that don't want to cross to the other side, but that would be very similar, except for the fact that here I need to tell you about the singularity as well. Okay, so these are all very good questions, but I'm trying to basically move to some other slightly different direction. So let me briefly remind you of the standard thermodynamics, what we learn in undergrad. So any thermodynamical system is described by some set of chemical potentials and some charges, entropy and the energy, and of course the temperature. And these charges and chemical potentials are related by the first law. Usually in thermodynamics, we have Gibbs-Duhem equation, which relates these charges and the variation of chemical potentials in this way. Together with the first law, we can basically integrate that and write energy as a function of charges, linear function of combination of charges, chemical potentials, and temperature and the entropy. Okay, so this is just basically for the change of taste. Now let's go back to this system that I'm considering. In our null boundary phase space, basically, I want to depict it as the thermodynamical phase space. If you remember, we had a d-1 dimensional surface, I mean, the sigma, and we had functions gamma and gi over there. And then the conjugate charges was omega and ji. Then I had P, which was among the noether charges. I mean, it was not among the noether charges, but it was appearing in the charge variation. It was in the flux. Then there was also the Nij, the graviton modes, and basically chemical potentials, which are basically this omega ij. This Nij basically tells me how out of equilibrium my system is, because it's like an open thermodynamical system residing at the boundary. Things can come and go. Okay, so that's basically the picture that I'm going to establish. I'm going to use the same equations that I had, but now reinterpret it in terms of this thermodynamical quantities. And I told you about the expansion parameter, which is another theta, which is basically another function which tells me whether I'm out of equilibrium or not. Okay, so just keep this notation in mind. This boldface calligraphic x for any quantity is the density of that object at NV. So this equation the charge variation that I have. This one, I'm going to rewrite this as the laws of thermodynamics. That's all what I'm going to do. So this is basically one of the equations, the same equation that I just showed. This is both sides of this are functions of v and xi. So these are generic functions on this codimension 1 null boundary. This Tn is the same factor gamma over 4 pi. For the stationary cases, this is basically the standard Hawking temperature. This is surface gravity over 2 pi. And this S is omega over 4g, the density of Bekenstein-Hawking entropy. J is the angular momentum. This is horizon angular velocity for the stationary cases. And these two are basically measuring how out of equilibrium we are. This is the first law of thermodynamics for an open system, but essentially is the same relation that I had for the charges. I've just rewritten this. Okay, so this is basically the first law for this null surface thermodynamics. If I have a non-expanding surface, theta equal to 0, let me show you this because I think this would be important again. Sorry for moving this up and down. So for the theta equal to 0, actually one can easily see that n should also be 0 to have a well-defined equation. So for the non-expanding case, n must also be 0. So I drop this and I drop this and I remain with a system which is stationary. It's basically closed thermodynamical system. Okay, when I have a non-expanding null surface. Then among these Noether charges, you can readily see that there is this relation, which is basically the charge associated by with d by dv is related to entropy and the angular momentum. This is basically this equation, just rewritten. This equation rewritten. So this is the same expression that I have. And this is the Gibbs-Duhem equation. Again, this is a local equation which is valid at each and every point on sigma. Okay. So these are basically the charges and the relation between the charges and the corresponding chemical potentials, which directly comes out of this covariant phase space analysis. It could be reinterpreted as the local laws of thermodynamics at the boundary. And let me emphasize that these equations are all written on shell. If I could have said it in a different way, that the same Ray-Chaudhuri and Damour equations that I just showed several times are rewritten in this way. So these are nothing but the same equations. Okay. In other words, these local laws of thermodynamics are nothing but the general constraints that the boundary degrees of freedom should satisfy. Or, in other words, the equations of motion for these local boundary degrees of freedom could be written as thermodynamics equations. Okay, so this is just the same thing written in a different inspiring way. And let me emphasize that these equations, although I didn't sort of show it explicitly, are just a result of the diffeomorphism invariance of the theory, and as requiring that the non-trivial diffeomorphisms which act at the boundary label the boundary degrees of freedom. So these laws of local laws of thermodynamics are just a manifestation of the diffeomorphism invariance at the boundary. Okay, so in usual thermodynamics, we also have a zeroth law that is a statement of thermal equilibrium, and the flow of charges are basically, as we know in usual thermodynamics, is related to the gradient of the chemical potentials. And if the gradient of chemical potentials is zero, basically flow of charges is zero, and we have a basically system in thermal equilibrium, and hence the zero law. So the question I want to ask is, in which sense this zeroth law could be satisfied in my system? First of all, for open systems where open thermodynamical systems, which are not in thermal equilibrium, we don't expect to have the zeroth law. So the question hence is, what's the subset of this system which keeps me in thermal equilibrium, and then there exists a notion of zeroth law. And this happens if basically the flux that I have is delta of something, some function over my thermodynamic phase space. If this is satisfied, then basically this equation imposes some relation between my thermodynamical quantities, and in that subsystem which satisfies this relation, we are in thermal equilibrium. So one can solve this equation. There's a bit of algebra. You can view this as a one form over this thermodynamic phase space, and then basically study integrability condition. I've just written it here. And the first condition that one notes is that the integrability condition is satisfied only if the flux of gravitons is zero. So this is a necessary condition for this to be satisfied. Or this.
I have a question.
Please.
Is Nij a constant, or is it a variable?
No. It is a general function over the sigma.
Right. So in fact, there are an infinite number of such charges, right?
Infinite in the sense, yeah, basically it's a function.
Yeah. Since it's a function,
yes,
it could be expanded in a Taylor series, and each of those coefficients would correspond to a separate charge, right?
Yes.
Yeah, correct.
Okay. It's a very good question. Let me come back to it later, a bit later. So basically, I can redefine this G in terms of this H in this way. This is basically the same equation. If such a G exists, the same equation could be written in this way. And this H should now satisfy these relations. So these are the integrability conditions. If you wish, this may remind you of a Legendre transformation over the thermodynamic phase space, and these are basically the Hamiltonian equations over that phase space, as you can readily see. So the integrability condition or the zeroth law is the existence of such an H. And in order this, and of course this, as I've already mentioned, Nij equal to 0 is a necessary condition for having this zeroth law. So I can still try to solve and see what these equations are telling me. And basically, this is a solution to these equations that I've written here. If there exists any H as a function of entropy P and J, H is not specified. And if I have this bracket structure, then these equations are satisfied. In other words, the zeroth law is nothing but the requirement that I have a well-defined phase space spanned by these charges. For example, S and P are just satisfying the Heisenberg equation, commutation relation, and these are basically the representation of S and P under J, and this is basically the angular momentum algebra. But these are all local. Okay, so the zeroth law is basically nothing but the fact that if I turn off the fluxes, I should remain with the well-defined phase space. So that's the physics of it. And this Hamiltonian, which is the boundary Hamiltonian, is not specified. So I was asked about the variation principle, the boundary term, and so on. That's a precise answer to this is in my setup is that to answer that question, specifically finding the boundary Hamiltonian is physically equivalent to specifying this H, which is the boundary Hamiltonian. So, and in my analysis, it remains unspecified. Okay. So one can show that for the stationary cases when I have the Killing horizon of a usual black hole, this zeroth law just reduces to the standard zeroth law that we are familiar with in the context of black holes and so on. So all these sanity checks are easily passed. So sorry for going over time. Let me just conclude. I told you that in presence of boundaries, we need to consider boundary degrees of freedom to account for whatever we are excising from the space-time. There are surface charges associated with the non-trivial diffeomorphisms, which can label these boundary degrees of freedom. And I use covariant phase space method as a systematic way to construct the surface charges and label the boundary degrees of freedom. And in particular, I worked out the charges in d-dimensional pure gravity on a null surface. I found d number of charges, 2 scalars and 1 vector. And hence my total solution space, or in the quantum sense, Hilbert space, contains boundary degrees of freedom plus the bulk degrees of freedom. And the boundary and the bulk degrees of freedom interact with each other through the continuity equations, the balance equation, the Raychaudhuri equations. These are all basically similar equations written for different variables. And but still, the dynamics of the boundary degrees of freedom remains free, and I need to choose them. I did it through this Hamiltonian, the boundary Hamiltonian in the end. In general, however, when I have fluxes coming through the boundary, I am dealing with a thermodynamic system, which is an open system. And let me emphasize, which this was related to several questions that I was asked. These equations, thermodynamic equations, are local equations at the boundary. So at each and every point at the boundary, I have these equations. So this is different than usual black hole thermodynamics, where you write down some integrated equation over the horizon. So these are local equations. But still I have this similar thermodynamic relation. And these thermodynamic equations are basically manifestation of diffeomorphism invariance of the theory. Okay, so I already discussed all these. I was asked a question by Subrat, which is partly related to the second law of thermodynamics. And that's basically whether the entropy that I have here, or the conjugate variable, the P, is always monotonically increasing. And one can basically sort of start from the usual focusing theorem and come up with some statements which is resembling the second law, but there are some details and issues that is in work in progress. So I hope we can basically sort that out. But I expect to have something like a second law, which is related to Sophie's question. The same analysis could be packed in a different way in terms of a memory effect, and in particular, a local memory effect or the horizon memory effect or the null surface memory effect. In one of our papers, we have discussed this. And basically, the idea is that the amount of the flux which passes through the boundary is related to the change of the associated charge. For example, for this P, so the same equation could be recast as a memory effect as well. This Raychaudhuri equation, for example. For example, if I integrate this over time V, this could be basically viewed as the total energy which has passed through the null surface, and that is associated with the variation or the change in the charge P. So this could be cast as a memory effect. So the same equations could be read in some different ways. Some of them have appeared in the literature, some of them maybe not. But in order to relate this to the question of black holes, I already mentioned that maybe the notion of the null surface is a bit too restrictive. I need to go to the stretch horizon and allow for the leakage out of this. And also I need to quantize this system. But now with this classical Hamiltonian system and the phase space structure, Poisson bracket, and all this, it is basically very right to do this quantization, and I hope we can go through this quantization. And once this is done, I hope that this can shed light on black hole microstate problem and hopefully on the information problem. Sorry for going over time. Thank you for your attention.
Thank you, Shahin. Thank you for a great talk. Let's all thank Shahin for keeping us engaged.
Thanks. Naveen, I can't hear what you're saying. Maybe it's just me.
Oh.
Can you speak louder, please?
Can you hear me now?
Yeah.
Mm-hmm.
Oh, I guess some microphone setting was. Is it all right now?
Yes,
it's good.
Okay, yeah. Thank you, Shahin, for a great talk. Let's all thank Shahin for engaging us for a greater part of 1.5 hours. It was a very great talk. So we'll take questions now, if there are any.
Can I ask a question, please?
Mm-hmm.
Could you please go back to slide 31, where you're talking about this Gibbs-Duhem or this local law? Yeah, right. So at the end of the day, this equation is really Einstein's equation projected in some along the horizon generator and along probably the auxiliary null generator and so on. Do you have some understanding how you would write it, just in terms of projections of Einstein equations or Einstein tensor in this case?
Oh, that's okay. So let me make a comment which could be partly related to your question. For the usual black holes, we typically have the smart type relation, and this could be viewed as a local version of that smart type relation.
Well, I understand, but I mean, this equation has nothing to do with black holes. This is really this is Einstein equation that is, in fact, it's local. So it's Einstein tensor projected along certain directions in a certain way. Some of those combinations you're calling E, some of those combinations you're calling other things. So once you have gone through all this, all this beautiful structure, then at the end of the day, my question is, once you have that equation, then do you know what, just in terms of the starting point, which is the Einstein tensor, what are all these quantities in terms of the projection of those tensors, of that tensor? I mean, the only structure you have introduced here is really one null generator of the null surface. And then probably you do have choice of the ingoing null that is actually used to parameterize, bezier constant surfaces and so on. Right. So everything in that equation is just, all the terms are just some projections of Einstein tensor along those vectors. There's no integral, there's nothing. It's just,
yes.
so I'm just curious to see what that thing is, because it has a nice physical meaning, it's like some things that in some situations you can call energy, something, some particular combinations, in some situations you can call pressure and so on. I mean, what momentum or is that?
Okay.
Yeah.
Well, that particular relation, unlike the first law, is not directly related to the Einstein equations. The first law does, but that one is not. It's just basically a relation between different charges and the associated chemical potentials. I can tell you individually what those charges are that you can see. For example, omega is actually, and I think this would be helpful to note this, is basically the scaling of, is related, the charge associated with the scaling of R direction. Remember that R equal to 0 is my null surface, and R is parameterizing how far from this null surface I am. Scaling of that is related to the charge associated with that is omega. The charge associated with the rotations on this null surface is, of course, as everybody would call it, angular momentum. And the charge associated with the motion, along this translation along the v direction is called E. So this equation is
but the equation,
some relation between some conserved charges and some geometric objects like gamma.
No, but I thought you said that the equation is local. It's true at every space-time point.
Sure.
Like, there is no integral. So there is no integral there.
No. Yeah, of course, there is no integral. The reason is basically, I just told you about the zero mode charges, but in general, if you want, you can look at equation 7. W, Y, I, and T are arbitrary functions, and I can take them to have a similar functional form. So then this means that this equation, the relation that I have written between omega and J, since these T, Y, and W are arbitrary, they should be local ones, right? So then I can drop the integral because these functions are arbitrary. Okay. So, but the sense of it, if you want to have a physical intuition, is better if you think about them as the zero mode charges, and then you can generalize it to be a local one, right? You can insert this W, Y, and T here. But I just gave this to build up some intuition. This equation, I think, is basically, although all these charges are written on shell, but that specific Gibbs to M type equation is a relation between these conserved charges and geometric quantities like GI, the angular velocity, and this gamma is sort of like surface gravity, if you wish, or the is related to the non-affinity of this null vector, which is generating the null surface. Okay. These are some geometric quantities. The first law is very explicitly a manifestation of Einstein equations, but this Gibbs to him is a bit different.
All right. Okay. Thank you.
I have a question.
Yeah. Go ahead.
Shall I go ahead?
Yeah, go ahead.
Yeah. So your xi that you had Q and xi in the previous slide that you showed, those parameterize the non-trivial diffeomorphisms, right?
Right.
So for each non-trivial diffeomorphism, you have a conserved charge. Is that right?
Yes.
So in general, you have a huge number of such conserved charges, right?
Yes, infinite number of them. Or
Yeah.
If you want to view them as some functions. Let me make a comment here. I didn't call them conserved charges. I called them always surface charges. And the reason is these are not conserved as long as I have this flux. So remember this balance equation. These are not conserved. These are surface charges, but not necessarily conserved.
Okay, fine. So, but in spite of that, in your final equation that you had, your zeroth law for thermodynamics, there you had the equation in terms of the Nij's, right? Those were, in general, a set of functions which parameterized the various charges, right?
Yes.
So, can't this be used in a certain way? I mean, can't you write a free energy with a chemical potential involving these charges and then differentiate with respect to the number and get the degeneracy or something? I don't know how the thing is done, but I'm guessing that this should sort of lead to the microscopic derivation of the Dickinson-Hawking entropy, right?
That's the hope. So we are not there. So to get there, we need to take two steps. Let me just start from the very basics. In general, we have this open thermodynamical system, but to use the standard stat-mech notions and thermodynamics, I need to go to some sort of equilibrium. And that's guaranteed by this zeroth law. So in general, in my phase space, where I have this omega p ji and nij, I have an open system. But the zeroth law is basically in which subsector I can define something like thermal equilibrium. And the necessary condition for that nij should be 0. Okay, so that's comment 1. The comment 2 regarding to your question is once we have some well-defined local notion of thermodynamics, then I can try to quantize this. And in principle, if I can successfully quantize this system, probably I get a handle on the black hole microstate and hopefully on information problem. But in order to quantize this, so this is we usually in quantization procedure, we start with this bracket structure, Poisson bracket, and then try to quantize this and promote these to operators on some inverse space and the rest of the story that you're familiar with. But the point is this Heisenberg algebra, that the local Heisenberg algebra is do not have finite dimensional representations. So you need to do something. This is what the problem that I call overshoot problem, right? You have infinitely many states which are all labeled by the same S and P. I want to have, I have way too many microstates which are all labeled by this because upon quantization, I don't have finite dimensional representations. We need to sort of add something to this system to end up with something finite. Some finite number of states. That's
but when you have a black hole, when you're considering black hole thermodynamics, you have a finite surface, right? So on a finite surface, you can always mode expand and get finite number of Fourier modes, which will correspond to finite number of charges. So even if you have to start with functions, they will end up being dual to some finite number of charges, right?
No, because these Fourier expansions, the Fourier modes go all the way to infinity. There are infinite number of them, right?
That's what I'm saying. I mean, if you have
we
a finite,
need to cut them off at some point, and that's exactly we need what I call a haircut for this software, right?
If you have a finite surface, on a finite surface, you can, for instance, if you have a finite interval, for instance, okay,
Yes.
If you have finite interval, you can Fourier expand a continuous function in terms of finite number of Fourier modes. That's what I'm saying. So if you have a finite surface, if you have a black hole surface, if you have a black
No,
hole horizon,
it is countable, but it is not finite. You need to have some UV cutoff as well, right?
okay, yeah, that's correct.
So that's you need something extra to be added to this blend.
Yeah.
Mm-hmm. So
Like,
please.
no, please go on. Yeah, complete, please. Yeah, I have a different question. Shahid, please complete. I was going to ask something else. I thought you
Okay. So I think this is a general problem or general issue with this Hawking-Perry-Strominger. If you want to really go through it and put it on the table, I mean, as a viable microstate identification mechanism, this is a general problem because this kind of algebras that one finds either at infinity or on the horizon on a null surface, these are infinite dimensional algebras. And they do not admit finite dimensional representations per se. You need to cut them off somehow. And you need
but
to
the
cut
Planck
them off.
scale would act as a cutoff, right?
No, actually, as you can see, Planck scale here naturally appears as my h bar. S and P commute to 1 over G, right? But this doesn't mean that we have a UV cutoff, right? We need something more.
But a UV cutoff will always be there, right? I mean, if you go to if sufficiently high energies, you get space-time foam.
No, but okay, so you're already bringing in other stuff, which I'm not sure if I mean we are allowed to do so. So these are all proposals, but they're not naturally a part of this structure that I just gave you. Let me emphasize, so far I just only used the standard diffeomorphism invariance and all what it takes. So I didn't include anything else. I didn't add anything else. So my point is we need to add something else to this system to be able to carry out the quantization. And we need to be able to do this in such a way that it's consistent with the basic setups that we used, namely diffeomorphism invariance. And I'm not saying that it is not possible. We have some proposals for this in three-dimensional examples, but I don't know how to work it through in general dimensions.
Yeah, classically it doesn't work, but finally, when you do the quantum analysis, you have to incorporate such things, right? Finally.
The question is, how do you define that quantization scheme? I don't have that.
Yeah, that's correct. Yeah.
Hi, Shahin. I have a different comment, different lines. So a couple of times in the talk, you said that to apply this to black holes in the quantum case, you need to generalize this to a time-like surface. I didn't understand why that is the case. You're right that the horizon in some sense is a time-like surface, but you know, if you you know, you could just continue working with a null surface, right? As you said,
right.
You have a null surface, and that null surface is slightly outside the horizon now. It's
yes.
but you could just continue working with that, right? And at least first order and perturbation theory, all that would change would be, I think, that the null energy condition would be violated when you include quantum effects. So there was this discussion we had about positivity and so on. So other than that, I don't see why you have to generalize the formalism to include quantum effects. I mean, maybe it's convenient to, but you don't have to, no?
Yes, right. By quantum effects, I meant something which is basically like a Hawking radiation, which is leaking out this. Right.
But why can't you do that in the null surface?
No, you can do that. But my comment was the natural way in the black hole setup in quantum black hole is to consider the stretched horizon and slightly move away from the null surface. But still, one can allow for the violation of the null energy condition and do what you mentioned. That's also one option. That's true.
Okay, thank you. Yeah.
Sir, I have a question.
Please.
Yes, sir. If we have one black hole in the space-time considered, will that form another null surface? for at least some region of the, or at least some region of the spacetime?
Sorry, would you repeat the question? I didn't get the question.
If the matter, if the matter in the considered region, if the matter in the considered region forms a black hole, would that
for
also
example,
consider
here,
as,
right?
as a null surface in here?
Okay, so if I had a matter, I would have included in my Einstein equations by addition of some extra term here, and here. Okay, so that would be the effect of the matter field.
Yes, sir. If that forms a black hole in the considered region, would that also, will that also to some degree constitute as a null surface?
Yes, I can still have that null surface, but I need to add the contribution of the matter in this too. That's true.
Yes, and could those thermodynamically react? And could those thermodynamically interact with one another?
Yes, of course. So let me again emphasize this. Here, if I add matter content to this, I need to add two terms here and here. That's one. And these are again projection of the energy momentum tensor. At the VV component of the energy momentum tensor would be added here. The VI component of the energy momentum tensor would be added here, or it's the divergence of that, I think. Okay, so but there would be some two terms which would be added here, and I need to extend my thermodynamic phase space to include the degrees of freedom associated with that matter field at the boundary. And then the rest of the story would go through still.
Okay, sir. If the two null surfaces interact, could there be a condition where the total and the entropy equivalent of the total system increases, but in one case it decreases and another increases? And what will be the physical significance of that kind of situation?
So this is related to the second law that I
Yes,
told
sir.
you, that one can extend the focusing theorem, and that focusing theorem is actually taking into account the matter field through Einstein equations, right? So that would be there in general, but what will come out of that focusing theorem analysis is that the area of something, or the expansion is have a specific site. So that's the general outcome of that kind of analysis. It doesn't take into account the different parts of the system separately. That's
okay. Okay. Thank you, sir.
Can I ask a question? Am I audible? Hello?
Please.
Yes.
Hi. So I maybe mentioned this, sorry, but I missed it. So is this null surface, like the boundary conditions you impose and so on, is the null surface allowed to radiate these fluxes back into the spacetime, or is it
no? So then, okay. So basically, technically, what I did was I just considered the most general form of the metric around this R equal to 0 surface, which is basically this one. And I assume that everything is smooth around this, and basically wrote down the Einstein equations and perturbatively solved it at around R equal to 0. So that was what I did technically. And what this means is that basically, if in this setup I can only take into account the infalling node rays. I don't know if I answered.
But you would want to complete this to include such effects, right? How, like, does this way of doing it allow you to do that, or?
Yes. In the pure gravity, that's all what I need. But for if you want to include extra matter, you need to put it in the T mu, and then.
I mean the null surface radiating gravitons. Is that?
Yes, that is included. So basically, that is already included. So something which you could have asked is, among the bulk modes, I had this Nij, which was the V derivative of this H, as you can see here, this gamma or in this, and then I had the this H prime. These are exactly the kind of gravitons which are moving along this null surface, and they do not appear in my thermodynamic analysis, the charges and so on. So I don't know if I answered the question. To be specific, so my gravitons have two polarizations, right? And they could be infalling and outgoing. So there are 4 modes. 3/4 of them are included in this Nij, and the 1/4 which is included in the H prime do not appear in this thermodynamic analysis. So,
okay. And I had
all kinds of gravitons are included in this sense.
Sorry, go on. Maybe I interrupted.
No. So I just wanted to give you a more intuitive picture of how this infalling, outgoing 2 polarizations of gravitons are treated here. All of them are
right. So you're saying the quarter of them don't enter the thermodynamic description, and
exactly.
Could you tell me again, like what is this particular quarter?
This 1/4 is H prime Ij. So these are basically part of specific polarization of the outgoing gravitons, which are moving along this null surface.
Okay, thanks.
But the reason is basically these kind of gravitons do not rotate under the diffeomorphisms that I just discussed. So hence they do not appear in this analysis, in the charge analysis, and hence the thermodynamic description.
Okay, I had another question, I mean, partially a comment kind of thing. So sometime like Professor Padmanabhan also had some kind of way of deriving, thinking of this thermodynamics of null surface and so on. Do you have any comment or comparison with how that program compares with yours?
Yes, sorry, I missed this. Which program?
There's Professor Padmanabhan who had like a program where he used to think about null surfaces and try to work out the thermodynamics of null surfaces.
Okay, good.
Do you have any?
In particular, are you alluding to Jacobson and whatever came out of that? I mean, after him?
I think my understanding is minimal, and I think it's slightly different from what Jacobson had. But I don't have. Yeah, I don't know.
Actually, in Jacobson's derivation of Einstein equations, he assumed that we have these thermodynamical relations, local thermodynamical relations at the null surface. Okay, and he had some extra assumptions which are a bit technical. For example, he assumed that we have a Clausius the heat equation locally at the null surface, and so based on these assumptions, he derived Einstein equations. So what we did here was basically try to shed light on that derivation, that these local laws of thermodynamics are actually coming out naturally. And what Jacobson, I think, missed, and I think is very conceptually very important, is that these thermodynamical laws, local thermodynamical laws at the null surface, are an outcome of diffeomorphism invariance and not per se the Einstein equations. If I had, for example, f of r gravity theory or Lovelock theory or whatever theory, which is not Einstein gravity, it is some other diffeomorphism invariant theory, I would have found the same local thermodynamics. So there should be something missing in Jacobson's derivation that lands him on Einstein gravity, not Lovelock theory, for example. Okay, so but in part there were some works by late Padmanabhan, Paddy, that he understood this, but his works basically had some other sort of shortcomings compared to what I just mentioned here. Paddy's works, which he did in several years, in the last 5-6 years, understood that this is coming from the diffeomorphism invariance probably, and is not limited to Einstein gravity, but he was integrating this over the surface of a black hole, or he was focused on the radial Einstein equations around a black hole or something like this. But our setup is very general, around any null surface, anywhere in the space-time, and makes it very clear that the diffeomorphism invariance and not the Einstein gravity itself is playing to get this thermodynamical equations.
Okay. Thank you. But like just to as a comment, like one of the things I remember Padmanabhan emphasizing is that his analysis works for general null surfaces, and he's not restricted to thinking about black hole horizons and so on.
Jacobson, yes, but he assumes this, and the very fact that he only gets Einstein equations tells us that he's missing something, because our analysis here, I didn't show it here, but if you did it for the Lovelock theory, you would have got exactly the same thermodynamical equations. Maybe the expression of the charges in terms of the background could be different, but for example, instead of omega, I would have had the Waltz entropy and so on, but the thermodynamical equation itself would be the same. The thermodynamic description cannot distinguish between Einstein, Hilbert action, and Lovelock. If Jacobson's derivation do not make this distinction, there's something missing in that derivation.
Okay, thank you.
Sure.
Can I have a question, if there is time?
Sure, yeah, maybe one short question.
Yeah, my question is, yeah, okay. Yeah, my question is about the decomposition between integrable charges and non-integrability. My question is, in other slicing, you call this a slicing thermodynamical slicing, right? So in other slicing, I mean, the first question is, the first slice independent of slicing?
Okay. Yes and no. So even the usual thermodynamics, you can choose different ensembles. You can have various different kinds of energy, Gibbs free energy, Helmholtz free energy, or many different sorts of energy you can define. And these are all, in my language, are just different slicings on thermodynamic phase space. So even the usual thermodynamics description is not slicing invariant. I mean, the explicit form of the equations are not written in slicing invariant. But we know that the physics of it is slicing invariant. So in the same sense, here we also have some thermodynamic slicing is not unique in no sense.
Oh, okay. So
this is one thermodynamic slice.
What do you mean? What is the other thermodynamical slicing other than choosing the noether charge? You mean?
Well, even that part is not unique, right?
Why?
So,
noether charge is unique, right?
Well, that's unique if you specify your slicing. The noether charge itself is also slicing dependent because it comes with the Xi, and you need to choose the Xi. You can call various different combinations of these noether charges a new noether charge.
Okay.
This is very much like a Legendre transform in the and choice of ensemble in thermodynamics.
Okay, thank you. Maybe later I can ask more.
Sure.
Thanks.
All right. If there are no more questions, let's thank Shahin again for a wonderful talk and an equally wonderful discussion after the talk.
Sure. Thank you very much. Sorry for going over time. I hope I didn't bore you.
No, it was great. Thank you.
Okay, thank you. Thank you very much. Thank you. Okay.
Bye.
Have a nice time. Bye.
Yeah, you too. I'll stop the call now.